Now we get to learn about connectedness, which is honestly one of my favorite topics in introductory topology, since I struggled so much with it when I was first learning it that I had to become like intimately acquainted with it, and now I have a fondness for it. So a topological space is called connected if this really weird definition works out. If there do not exist disjoint open sets, U and V, which partition the space. Okay, another way to phrase that is your space is connected if you can't split it into two parts. Right? So hopefully that makes sense. A connected space means it's one solid unit rather than two or more. But if you try to work with this definition, it's absolutely hideous. Showing there do not exist certain sets is really hard to do directly. Usually you have to phrase things by contradiction and instead say, suppose your space is not connected. Okay, well, if it's not connected, then it's what we call disconnected. And disconnected would mean there do exist disjoint open sets U and V which partition the space. And so to be formal, since we work with disconnected more often than we work with connected, for the reason that it's such an ugly definition. So to be formal, there are three properties. To be a partition, your sets have to be non-empty. Okay, so I specify U and V are non-empty. This condition here means they're open. So here I'll just say non-empty open sets. Their union is the whole space. So you can say they cover the whole space. Otherwise, if you're missing a point, you're not partitioning the space. And they're disjoint. Their intersection is empty. So these three things together give you what's called a disconnection of X, otherwise phrased U and V disconnect X. They break it apart into two separate chunks. Great. So that's somewhat easier to work with, although it's not my favorite definition of disconnected or connected, but it's somewhat easier to work with. So pictorially, what's happening is a space like this, that's your X, that would be connected, because you certainly can't split it in half into two open sets, right? You could split it so that like one half was open, one half was closed, but that's not sufficient, right? You need two open sets. So that would be a connected space, whereas something like this, let's say I just drew two blobs. So that's A, that's B, and X is the union of these two, so just those two together. That is disconnected because I guess I could have called them U and V rather. Lo and behold, you have two open sets U and V that are disjoint from one another, and their union is everything, and they're not empty. So I mean, it means what you think it should mean. Disconnected means two separate blobs, or at least two separate blobs, whereas connected means one cohesive thing. Great. Another way to phrase it, though, is that a topological space is connected if the only Clopen sets are the empty set in the whole space. So we already know that these are automatically Clopen, both closed and open, no matter what your space X is. But in fact, if you're connected, those are the only ones. And that can be seen as follows. I mean, imagine if I had, let's get weird with it, make it, half open, half closed kind of nonsense. That's U, that's V. And we're calling X the union of those two. This certainly looks disconnected. And you can claim that these are both Clopen sets. Since they're not empty and they're certainly not the whole space, the fact that there exist any other Clopen sets means disconnected. And I'll just mention they're Clopen because, as subspaces, they're sort of relatively closed and relatively open. The fact that they're separated means you can actually, fit open sets and closed sets intersecting each. Cool. Similarly, I could have drawn, back to that nice example. Here was U, here was V. This is nicer. I mean, they both look open, so I don't have to worry about the subspace topology or anything. They both look open. Why are they both closed, though? Well, they're both closed because V is the complement of U, and U is the complement of V. And the complement of an open set is a closed set. So they're both open and closed. Cool. Whereas if you had a connected space, so here's some connected blob, then, okay, certainly the whole space is Clopen, certainly the empty set is Clopen, but if I picked any subset here, no matter how I'm drawing it, some subset, U can't be Clopen, right? If it were closed, its complement would be open. If it were open, its complement would be closed. And since it's a connected space, it's not going to be able to be both. So the only Clopen sets are the empty set in itself. So sometimes that's a handy definition of connected. It's certainly nicer than this one up here, which talks about the non-existence of a partition. So yeah, you can check Clopenness if you want. Though my favorite definition of connected is this. So we have to define a discrete space. So I'm going to call it D. And I'm just going to give it 2 points. I think you can do more than 2 points if you want, but it's easiest to understand in the case with the points 0 and 1. And we're going to endow this with the discrete topology, which I'll call tau sub D. Remember, the discrete topology means every subset of D is open. So the empty set's open, the whole space is open, the singletons 0 and 1 are open. I think it's worth writing that down. Tau D equals the collection containing the empty set, the singleton 0, the singleton 1, and the whole space. And nothing else. Those are the only open sets in my discrete space. Then it turns out that being connected is equivalent to all continuous maps of this form being constant. And this is an absurd definition. It's real weird to see where it comes from when you first encounter it. But here's the way I like to explain it. I like to think of 0, 1, my discrete space, as giving me a sort of height. Right? So I'm thinking about my function, taking some, surface, and giving it a height in R3 maybe. So for example, if this is my domain X, and I think about some continuous function on X that either outputs 0 or 1, it's just going to give me a height map, like an elevation map on this contour. Okay, so what's going to happen? Well, imagine somehow it was 0 at some place and 1 at some other place. So let's say it had, height 0 here and height 1 here. What does that look like in R3? Well, here's that part of the blob. Maybe I should try to draw it in perspective. I don't know, that's as good as I can do. That's a blob at height 0. But then at height 1 is the rest of the blob, and it sort of disconnects, right? You have to tear it apart to get that. And so certainly the function f that mapped x to d can't be continuous. I mean, you're tearing it apart. That violates our whole intuition behind what continuity is. Continuity says you're not allowed to tear things. And so maybe this should be further over here. Yeah, there you go. I'm trying to say, like, there's this height gap of 1. They are actually torn apart in R3. And so that's why connected spaces actually have to map to nice flat regions in R3, if you're thinking about it that way. Meaning the height map, the function f has to be constant. So this is bad. Not continuous. But if you were to apply a continuous map, then either this would happen and everything would be at 0, or the alternative would happen, and if it's the constant function where it's always equal to 1, you would get that it's sitting at height 1. And the drawing's kind of ugly in that sense, but imagine all those points are at height 1. So any continuous deformation of this can't break it apart. It has to sit at exactly one of those, in exactly one of those planes, either at 0 or 1. So that goes to say continuous implies constant for all maps to the discrete space if your domain is connected. What happens if it's disconnected, you might ask? Well, if it's disconnected, you get something like this. Right? So we'll say that's U, that's V. U gets mapped to 0 and V gets mapped to 1, maybe, right? So this is some function f where it assigns, zeros to every point in U, 1 to every point in V. So I'm thinking about that as height 0, height 1. And this is okay. I'm actually not tearing anything, weirdly, right? Because they were split apart to begin with. So it turns out that you can define a continuous map here. And if you don't believe me, consider any open subset, right? Any open subset I take is going to pull back nicely. So say I did, some open set here and pulled it back, it would come back to this nice open set. And yeah, the preimage of every open set is going to be open. That's a bit misleading the way I drew it. In actuality, you're just mapping to the space 0, 1, right? This is just a visualization to help intuition. But you can say that the preimage of 0 is actually U. Right? The set of all points that map to 0, well, that's the space U, the subset U. The preimage of 1, set of all points that map to 1, well, that's V. And by the discrete topology definition, both of these are open sets, right? Everything's open in the discrete topology. And certainly both of these are open. For the same reason we discussed above, you can, fit some open set around it in R2 or whatever your space is and call it relatively open. And same for V. And really, to check continuity, you have to check that every preimage, every open set has an open preimage, but the only other open sets are the empty set and the whole space, and certainly The preimage of the empty set's the empty set, which is open. The preimage of the whole space is the whole domain, which is open. So that's how I think about connectedness. Sometimes this comes in handy, this weird definition. So instead of trying to find a disconnection or trying to prove no disconnection exists, you prove that, given some continuous map from your space to the discrete space, it has to be constant. It doesn't always make the proofs nicer, but sometimes it does. Anyway, that's it for this video. I guess I could mention offhand that connectedness is a topological property. I mean, it's preserved by homeomorphisms. So if you ever wanted to check if two spaces were homeomorphic, you could check if they were, if one of them was connected and the other wasn't. If one space is connected and the other is disconnected, they can't be homeomorphic, because how do you get from a connected space to a disconnected space? Imagine the continuous transformation you'd have to make. Eventually, you're going to have to split this pair of pants in half, and tearing is not allowed by continuous maps. So certainly not allowed by homeomorphisms. Anyway, that's it for connectedness. Thanks for watching. I forgot I have some more examples. So if we deal with the real line with Euclidean topology, it turns out that connected is equivalent to being an interval, whether it's a closed interval, an open interval, half closed, half open, or even an interval that goes to infinity in one direction. It's still connected. And that's an if and only if statement. All intervals are connected, and all connected subsets of R are intervals. In particular, if you took something that wasn't an interval, it would certainly be disconnected. There's U, there's V. They're definitely not. Or sorry, I guess, yeah, if we're calling X the union of U and V, then X is certainly not connected, and it's certainly not an interval. So those are one and the same. You're working on the real line. If you want to get a little weirder and think, what about the discrete and indiscrete topologies? Then what happens? Well, indiscrete means our only open sets are the empty set in the whole space. And so naturally, everything is connected. Remember, indiscrete meant we couldn't distinguish one point from another. You can't put one in an open set and exclude another point from that same open set. The only open sets are the empty set in the whole space. So there's no distinguishability between points. And so, yeah, everything has to be connected. I mean, if you tried to form a disconnection, what would you have to do? You'd have to be like, okay, given this point and this point, maybe, try to find some open sets disconnecting them. But guess what? The only open set containing either of those points is everything. So you can't disconnect it. They're all glued together inextricably. So keep that drawing. Whereas on the discrete topology, your space, no matter what it is disconnected, because you can always separate it into a partition of two open sets. That's an open set. That's an open set. Everything's open in the discrete topology. So yeah, you can find any pair of open sets really that partition the space as long as they cover it and they're disjoint. I mean, you could have taken a singleton and then the rest of the space. That would be a partition. And so disconnect it. Since you can do this for any subsets you want, since you can take any pair of points and be like, hey, I can disconnect X around those points, we call it totally disconnected. Basically, that means that the only connected subsets are singletons. Right? Singletons are sort of trivially connected because there's only one point, so there's really nothing to check. But if you're totally disconnected, the only connected subsets are singletons. So yeah, you're totally disconnected because any point can be hidden from any other point. It turns out there are some interesting totally disconnected sets. For example, the Cantor set, if you've seen that in real analysis, is formed by taking the closed interval from 0 to 1 and repeatedly removing the middle third. That's a third, that's 2/3. And then on each of those chunks, remove the middle third and so on and so forth. The Cantor set is what you get in the limit as you approach infinity. That ends up being totally disconnected because, again, any pair of points you pick, you can find a disconnection with them. And yeah, the only connected subsets of the Cantor set are going to be singletons. Another way of saying that is the Cantor set contains no intervals. Of course, the Cantor set has a lot of other unintuitive properties, like it's uncountable. There are uncountably many points in the Cantor set, and yet it has measure 0, which maybe you haven't seen measure yet, but it in some sense tries to capture the notion of length. So there's almost nothing there, but there's uncountably many things there. It's totally disconnected and has a lot of other wacky properties. And then perhaps more intuitively, if you take Rn with n greater than or equal to 2, you can subtract a countable number of points and you're still going to be connected. Right? Say I deleted all these red points in R3, I'm still connected, right? I can still get from any point in the space to any other point in the space. So I'll still be connected. All right, and that is it. Thank you for watching.